Hello, we will talk now about two basic strategies to traverse all the nodes in a graph, or to visit them systematically, which is the meaning of traversing, of graph traversal. We have heard about two basic strategies. One of them is called breadth first search, and that is in which we select a starting node and then we take all those immediate neighbors to that starting node. We put the starting node in one level, let's say level 0, and then we write all its neighbors in the next level as long as we discover them, and then we just make another level with all those nodes that are discovered when as neighbors of those in level 1 on the previous level, and we write them in level 3, and we discover all of them level by level by level. There's another strategy called depth first search, in which we also start from a given selected node, and then we visit one particular child of that node, and a child of the child, and then a child of the child of the child, and so on. And so we build in depth, and then we backtrack recursively to visit all the other nodes that haven't been visited, but always going depth first and then backtracking, and then depth first and then backtracking. And that is another strategy. In the end, you end up visiting all the nodes of the graph, whichever strategy you choose. Let's take a look at the implementation side of this problem, since you already know the main basic idea of at least breadth first search. Now, so look in this, what do we have in this code, this pseudo-code? Well, we first know that we need to initialize one structure, which is a first in first out queue with the beginning element, with the starting element, and this queue will contain all the pending work, all those nodes that are pending to visit. That's what we will use S for. Then if you look at some other parts of the code, you will see that we need to check always. Remember that it is very important to check that whenever any nodes are discovered, we need to check if we have explored them or not, because if we have, we won't explore them again. So that check is here, is done here when we compare the corresponding element of the explored array to be false or true according to whether the node has not or has been visited before. So in this case, we need to initialize also the array, the Boolean array, as the FIFO queue. So let's do that. I will initialize first I will refer to the explored array, and we'll refer to this as a simple array which is indexed with the numbers of the nodes, and initially all of them are set to false. Then I will represent the set S, which is just a FIFO, a first in first out queue, and that will be represented as this long channel. You'll see why. But a queue has an input side and input side, and all elements enter the queue through the input side and exit the queue through the output side, all the way out on the other side. We will also keep track of the nodes visited. We haven't added those print statements in the pseudocode, but it's easy to see where to put them. And then let's begin. So initialize S to be a first in first out queue with one element S, the element where we are beginning the search. Let's choose one particular node for that to begin with. I'll say node 1 will be the beginning, so the S will be 1. So this node 1 would enter the S queue and will be ready in here to get out. So that's the initialization phase. In fact, it's not S, it should be 1. Node 1 is the first one, the starting node. So we go back and we see. Next we have a while loop. This while loop goes from here to here and it has this condition. While S is not empty, And right now it is not, because we just initialize it to be the starting element, the starting node. Take a node u from S. Okay, so we take an element out of the queue. This would be take element 1 from the queue. So now it's here, out of the queue. Now we check if explored of u, the element we just took out from the queue, explored of 1, is equal to false, then we have something to do, which are all these statements. The first one would be set explored of 1 equal to true. So in this case, we see that if this position of the array explored is false, which indeed it is, we set it. Notice that at this time, we are sure that we have visited that particular node, node 1. So we can say that 1 is the first node to be visited with all confidence. Now, we are at this point now, and we need to perform this loop. For each edge incident to the first node, or whatever node we are considering, add v, which means the neighbor, to the QS. Add all the neighbors to the queue. So let's do it. Look, and we do that by looking, how do we get all the neighbors? Well, for this one, we are indexing this list of lists, well, this array of lists, and we look at the list for array 1. I mean the list for node 1. So the elements in this list are 2 and 3, and those are the ones that enter. Say 2 comes here, right there, and then 3 comes here also, through the input to the output. And now we go back to the pseudocode. So since we exhausted all the edges incident to this particular node, we find ourselves in the end for. Takes us directly to this end if. By the way, this if statement has this scope, and then so we go to the end while and back to the beginning of the loop. While S is not empty, take a node u from S, and we see that in fact it is not empty. So we will take a node from it. The next node that we can take out of it is 2. And now we are back to this part. We check if explored of 2 is false, then set explored of 2 equal to true. This means if we have seen this element before, if it's true that we have not seen this element before, we marked it as seen, as explored. So the index for 2 in the explored array is false, so we set it to true. And now we check all edges or all neighbors incident to this node and add them to the queue. So we're looking at element 2. So we look at the second list and we add all those elements, which are 1, 3, 4, and 5. So the first element is this one. It would enter the queue and get in this place. And then would come the node 3, and then 4, and then 5. And we reached the end of the list. So we have no more neighbors here, no more edges. And we found ourselves with, at this end, 4. We just have completed the for loop. So go to end if and while, back to the beginning of the outer loop. While S is not empty, take a node u from S. So the next node to be taken out is node 3, and now we need to check if it has been explored or not. If it has not been explored, then we set it as explored and do all this work. It turns out that node 3, if we look in the explored array, the corresponding position is false, so we set it to true. And we know, oh, by the way, we have then discovered 2 and 3 in that order. And so we go back here to this place and see that we set explored equal to true. Now we need to add all its neighbors to the queue. So all the neighbors of 3 we need to be taken from this list, from its list. And we have this 1 first, which would come this way will be introduced here. And we have still more coming. This next we'll have this 2, which will come over here, and then we would have 5 coming in, and then 7, and then 8, and then we reached the end of the list. This means that we have completed this for loop. We are at the end for, at the end if, at the end while, and go back to the beginning of the outer loop. While S is not empty, take a node U from S. So what is the next node to be taken out of the queue? It will be node 1. So we have 1 again. Then we should check if the explored array in that position is false. Then we have something to do. But in this case, we see that 1 has already been visited. So this condition explored of U equals to false is not true. So we would go to the end if right here, then to the end while. So we ignore that element and take another one if the queue is not empty. That's indeed the case. So the next one to come out would be element 3. But the same thing, if we go and check explored of 3, we see that it is true. So this condition is not true. That means we go to the end if and while. So we basically ignore the element and take the next one. The next one to be taken out is 4. This time we check explored of 4 is false. Since it is false and we are visiting it, we set it to true. At the same time, we may write it here as the next node to be visited. So then we are here in this part of the pseudocode, and we need to go through the loop that adds all the edges or all the nodes at all the neighbors of this particular node 4, and we find them here in this list. 4 has only 2 neighbors. So those neighbors are 2 and 5. So imagine the 2 coming first into the queue, and then we would have the 5 coming in. So, and there are no more elements in this list. So we just completed the for loop, and if, go to end while, back to the beginning of the outer loop. Well, S is not empty, take a node U from S. So the next to be taken out is 5. Take out node 5, and then we need to check if it has been explored or not. And if it has not been explored, then we set it to explored. So we see that for 5, explored of 5 is false. So we set it to true, and this would be our next node to be visited. And we are over here in the pseudocode. We need to enter the loop. So that means that we need to go to the list of element 5, find all of its neighbors there, and place them one by one in the queue. So the first one to be enter the queue would be 2. Node 2, and then 3, and then 4, and then 6. And then we have reached the end of this list. Nothing else to add. So we are here. We go to the end if and while. Next round on the loop, on the outer loop. While S is not empty, take a node U from S. So the next node to be taken out of the queue would be node 1. But you see, if explored U equal to false, we would have something to do. But it turns out that this condition is not true, does not hold, because 1 has already been explored, and this is true. This means that we go to the end if, to end while, and back to the beginning. While S is not empty, take a node U from S. So next node to be taken out from Q is 2, and we have the same thing happening because explored of 2 is true. So we need to skip it basically and take another element from the Q, which is 5, and then we check now that we have already visited that one, so we need to skip it and go to take another element out, which would be 7. Now this 7, explored of 7 is false. So in this case, the condition for the if is true, because explored of 7 is false. So we set it to true. This one, 7, we set it to true. And then we perform the for loop by looking at that particular list, the one for 7, and then getting all the neighbors from here into the queue. So the first one to come in would be node 3, and then node 8, and then 3 and 8, and then nothing. We just finish the for loop, and if, and while, and go back to the other loop. While S is not empty, take a node U from S. So next node to be taken out from here, from the queue, is node 8, and check if explored of 8 is false, then set it to true. We just do just that. So it turns out that explored of 8 is false, so we set it to true, and that means we just visited it. Oh, we haven't written that we have visited before 7, and then we are visiting 8 now. And so we look, now we are in this position in the pseudocode. So we go and perform the for loop, and it means that we need to look at this particular list, the list of node 8, the list of neighbors of node 8, and we have that list of neighbors being consisting of 3 and 7, which would enter the queue, and in this order, 3 first and then 7. So at this moment we are done with the for loop, and if and while, back to the other loop, and take a node U from S, take another node out from the queue, which is node 2, and check if it has been explored. But it turns out that 2 has already been explored, so we skip this node and we take the next out, which is 5. But it turns out that 5 has also been explored previously, so we skip it and we take 2 out next. But 2 has already been explored, which means skip the cycles and go to the next node that can be extracted from the queue, which is 3, and it turns out that node 3 has already been explored, so we skip that one and take the next one out, which is 4. But 4 is also an explored node, so we take the next one out, which is 6, and when we check explored of 6, we see that it is false. In this case, we set it to true and perform the for loop. So we set 6 to true. We now know that this is the next node to visit and get its neighbors in the list, or in the queue. Its neighbors would be, the neighbors of 6 are found in this list, and we have only one single neighbor for node 6, which is 5. So that's the one we introduce, and we're done with the for loop. And if and while S is not empty, take a node U from S. So it's not empty, so we take the next one out, which is 3, and check if it has been explored. So it has. Then we skip that one and take the next one out, which is 8. Turns out that 8 has been explored already, so we skip it and take the next one out, which is 3, and then we check explored of 3. We see that it has been explored before, so we basically skip, do nothing, no work at all, and take the next one out, which is 7. But it turns out that 7 has also been explored, so we take the next one out, which is 5. And then we check that 5 has also already been explored, so we would skip that one and take something out from the queue, but the queue is now empty. So we're now in this place, while S, we check that S is not empty. This would fail because it is now empty. So we end the while loop and we are done. And the order in which the nodes were visited in this case was the following. The first one to be visited was 1. Then we visited 2 and 3 in that order. So 1, then the order in which we visited them would be this one. 1, 2, then 3. Then we visited 4 and 5 and 7. So 4 and 5 and 7. 4, 5. But this is the sixth one to be explored. And then 8. And then 6 was the last node to be explored. Okay, so let's take a look at the complexity of BFS, the breadth first search. If we look attentively to the algorithm, we distinguish actually 2 stages or 2 steps. Step 1, initialization, and here I remind you that we not only initialize S, which is a simple FIFO queue with only one element S, but we also initialize the Boolean array explore of U, which has n elements. So this initialization, at least because initializing this to false is a loop that would take us big O of n, then the complete initialization stage would take big O of n. Then the second part is comprised by these 2 loops. The inner loop takes a look at all the neighbors of a particular node V, and checks them all basically by chasing or checking each of the edges. Okay, so, and it does that for all the nodes. So in a first instance, let's say we have these 2 nodes, V and W, and the algorithm will check each of the nodes adjacent to each of the edges adjacent to each of the nodes. So that means that when we are looking at node V, it would check all these edges once. But when we are looking at node W, we would be checking also at each of the edges once, with the result that each particular edge is counted twice or checked twice, once for this node and once for this other node. So in the end, because we end up checking all the edges of all the nodes, that's equivalent to add the degrees of each node U for each U in V, a set of vertices, and we know that that is 2m by the argument I just mentioned, because each edge is really checked twice or counted twice. When we count the degree of each node and we add all those degrees, we basically count each edge twice. Once when we check the degree of one node in one of its ends, and the other time when we count the degree of the node in the other end. So the complexity of this process is 2m. We might say big O of 2m. We might, because of the 2 might be absorbed by the constants involved in the big O notation and concept. This is really big O of m. So that's the complexity for step 2. Big O of m. And if we add those two complexities, we have big O of n plus big O of m. We can just downright say this is big O of m plus n. And this is the complexity of BFS. S to be a LIFO stack with only one element, which is the starting node. In this case, the starting node is 1, so that node 1 would enter the stack right into the bottom. Then we enter the main loop. So we also have a main loop, and we have an inner loop, and we have an if statement with only a positive branch and no negative branch with this scope. So back to here. While S is not empty, take a node U from S. And S is not empty because we have just added 1 to it. So we pop the stack and we get 1 out of it. Node 1. Then we need to check if explored of 1 is false, then we have something to do. And this will be the case because node 1 has not been explored, so explored of 1 will be false, which means this condition holds. This will be true, so we need to set explored of 1 equal to true and then add all of its neighbors to the stack. So that would mean set this value to true. That means that we have just visited node 1. That's the first one to be visited. And now we need to go to the corresponding list and take all the neighbors of node 1 from that list. Initially, we have only 2 and 3. Okay. So since we just popped the stack, we have an empty stack. So when we now push element 2 and then 3 on top of it, and we will have 2 and then 3 in the stack. And we're done with that list, so we are in this end for send to the end if to end while S is not empty, pop one element from the stack. That element will be 3. And then check if explored of 3 is false, then we have something to do, which is set it to true. So explored of 3 is false, we set it to true. And we still have something to do, because now we need to add all of its neighbors to the stack. And where do we get the neighbors for 3? We need to look at the corresponding list. So, and we have the first one to be discovered would be 1, which would be pushed into the stack. And we would have 1 here on top of 2, and then 2, and then 5, and then 7, and then 8, and that's the end of the list. All the elements, all the neighbors of 3. So we are in this place. And if and while, well, S is not empty, take a new node out from the stack, so that new member would be 8. Then check if export of 8 is equal to false, and set it to true and add all of its neighbors to the stack. So look at for element 8. In export of 8 it is false, so we set it to true. By the way, the next I forgot to write node 3. Now we are looking to node 8 and we set it to true, and we know that the next node to be visited is 8, and we look at its corresponding list over here, all the neighbors. We add all the neighbors of 8 here, which are 3, and then on top of it we would have 7. So you have 3 and then 7. Okay, then, and we're done with the list. We're here, and for, and if, and while s is not empty, take a new element from the stack. So the next one to come out would be 7. Then if export of 7 is false, then we have something to do, set it to true and add all of its neighbors into the stack. So we see that indeed, if we check, export of 7 is false, so we need to set it to true, and this would be the next node that we visit. And now we need to add all the elements of node 7 to the stack, and where do we get them from? From the corresponding adjacency list. So we have 3 first and 8 next. So 3 would come on top of everything in the stack, and then 8 on top of 3. And we are done with the for loop. So enter the main loop again. If the stack's not empty, pop it, and we would get node 8. Okay. In this case, if export of 8 is equal to false, then we have something to do. But in this case, as you can see, export of 8 is equal to true because it has already been visited. So we don't do anything. We go back to the main loop, pop another element from the stack. This time it will be 3. But when we look at if export of 3 is false, we see that it is true, that it has already been explored. So we don't have anything to do. We just need to pop the next number from the stack. And this will be number 3. Again, sorry, 3, I forgot to cross 3. 3 had already come out. So it will be again number 7 for the second time. And when we check 7, we see that it has already been extracted from, already been visited. So we go to the next one, which would be 5. When we check export of 5, we see that it is equal to false. So we set it to true. We know that it's the next node to be visited, and we now need to take all of its neighbors from its list, and its neighbors are 2, 3, 4, and 6. As they are found, they are pushed into the stack. So we would have 2 and then 3 and then 4 and then 6. Okay, and then when we reach the end of the list, we'll reach the end of the for loop. So in if and while, go back, we'll pop another element. This time the element we pop is number 6, and we check If explored of 6 is false, yes it is, so set it to true, and this will be the next node we have visited. And so now we need to add all of its neighbors, all the neighbors of node 6, and are taken from the corresponding list, and we have only one, which is 5. It goes on top of everything on the stack, and we reach the end for and if and while, go back again. If S is not empty, take a new element from S and see if the corresponding node has been explored. So the next thing to come out of the stack would be the one at the top, which is 5. And we see that this has already been visited, so it means that we just skip everything and pop the next one we can pop. That would be 4. This time explore the 4 is false, so we set it to true, and that will be the next node to be visited. And now we need to add all of its elements from its list. Okay, so this is a list for 4, and we have 2 and 5 being the only neighbors for node number 4. So we introduce them in the stack, push them. Oh, that was a 5, not a 3. 2 and 5. Okay, so we're done with that list. Again, we are done with the for loop, and if and while, go back, pop another element. This time we pop node number 5 and look at explored of 5. It is true, so we have nothing to do. Pop some other node from the stack. This time we pop number 2, node number 2. So node number 2 is taken out of the stack, and now we check explored of 2. This is still false, so we set it to true. This will be the next node to be visited, and we need to add all of its children or all of its neighbors into the stack. So take a look at number 2's list, and we have the neighbors being 1, 3, 4, and 5. And when we push them into the stack, we would find 1, and then 3, and then 4, and then 5. Okay, and according to the code, we are in this place, in div, in while, go back, take a new node from S. So the new node we can pop will be the one at the top, which is 5. Then look at explored of 5, and we check and we see that it is indeed true. So we have nothing to do. That means we need to pop another element. We didn't do anything. So we skip 5 and we pop the next element, which will be 4. Okay, so 4 is next, and explore the 4 is true, so we skip it and we pop the next one, which is 3, and we check that explore the 3 is true, so we skip it sorry. So this 3 would not be, we pop the next one, which is 1, and then explore the 1. We see that it is true, so we need to skip it, and we pop the next one out, which is number 3, and in fact we'll find that 3 is also true because it has been explored already, so we need to skip, and we keep pop the next one, which is 2, and explored of 2 is also true, so we need to skip that one too, and pop the next one that can be popped, which is 2 again, and of course we'll need to skip it, so we pop the next one, which is 1, and 1 has already been explored, so we pop the next one, which is 2, and we check that 2 has already been explored, so the next time we pop the stack, we have an empty stack, and we reach the end of the while loop, and we're done. So this is the traverse path. You see, it's a very different path from the breadth first search. This is DFS, and let's take the color green to sort of track the traverse path. So started in 1, then we went to 3, which is a child of 1, then we went to 8, which is a child of 3, then we went to 7, which is a child of 8, then we went, 7 has no more children. The only children it would have, or the only adjacent node, is 3, but we have already visited that, so we need to backtrack, and the algorithm naturally backtracks from 7 to 8. 8 discovers no new nodes, then goes back to 3, and from 3 we discover a few new nodes, which is, one of them is 5, and that is the next one to be visited. You see 1, 3, 8, 7, then we backtrack up to 5, and then from 5 we discover 6, which is a child of 5, and then 6 has no children, so we backtrack to 5 again, and 5, we're looking for a neighbor of 5, and we indeed, so we have already discovered 6, and that neighbor would be 4. Okay, so we are over here, and from 4 we discover node number 2, which is the last one to be discovered. And this is depth first search, and you see how it's looking to the maximum depth and then backtracks recursively. The recursion is achieved through the LIFO stack. So when you see a last in first out stack, it is naturally occurring for recursive programs. It's a way to implement recursion in a linear fashion. So this is DFS, and hope you can enjoy making more of it, going through more of these exercises. If you implement it, stay close to the pseudocode and make sure that you have some operations like this one, checking if an element has been already explored or not. If you implement it as an array, it would be practically constant time. Direct access in an array is very fast, so it is very efficient to use this representation, a Boolean array, to keep track of the visited nodes, of the nodes that have been explored. Then the stack does the recursion, and the rest of the code takes care of everything else. And note also that both of these algorithms, the BFS and DFS, are depending for their efficiency to the adjacency list representation. We wouldn't be able to achieve the bounds we achieve, because of course this other implementation, if done properly, would have the same complexity as DFS. So well, it depends also on the nature of the graph. If you have a very connected graph, or if you have in particular configurations, one element would perform better, one algorithm would perform better than the other, but it depends on the connectivity of the graph. So one is good for some purposes and the other is good for some other purposes. And you will see that in applications. In the first, the simplest examples of applications of artificial intelligence involve searching, and we have at least these methods to search to begin with. So make sure you understand them and you enjoy them and you come to like them and you can code them properly. Thank you very much.